Hello, here in this we're going to look at 5.3 inverse functions and relations. Here's the why. Inverses are the key to going backwards and forwards from a rubric or formula standpoint. There's lots of situations that we use in everyday life, such as driving forward and then going in reverse, that involve opposites. Sound canceling headphones, if you look into the technology on that, create opposite sound waves to counteract the sound waves the noise you're trying to cancel. Inverses are also going to be helpful for solving for a different part of a formula, to where all the information is the same, but you're able to view it from a backwards perspective. That's what inverses are all about. We're going to be learning about how to find inverses, what inverses look like, how we can use them. All of that stuff will be happening in 5.3. Here's some examples of some formulas. You may be familiar with this one from geometry. A squared plus b squared equals c squared, where c is the hypotenuse of a right triangle. We have y equals mx plus b. This is distance equals rate times time. All of these formulas are solved for a certain variable. Right, like this formula is solved for distance, this one's solved for the y-coordinate, this one's solved for the hypotenuse. But you very well know, a lot of times in geometry, you needed to solve for one of the legs of the triangle, given the hypotenuse. So one example of inverse would be taking this equation and simply solving it for another variable. So let's solve it for a. So I'll subtract b squared from both sides. And then when I go through and square root both sides, we'll get that a is equal to the square root of c squared minus b squared. Now this formula and this formula are the exact same. It's just that this one has been rearranged for a. And this would be very useful if we had a lot of triangles and we knew the hypotenuse in one leg but we didn't know the other. If I gave you a whole bunch of different triangles and you knew what the hypotenuse was, but you needed to know this side length A, our new formula would be very helpful to help us find those side lengths very quickly. So that's another thing that you'll use inverse formulas for, is to rearrange a formula to make it to where it's not solved for the particular variable anymore. We're allowed to rearrange it to where another variable is in focus. Similar to your car. You can drive it forward, but sometimes you need to switch it gears and accomplish something from another perspective and go in reverse. All right, so here you'll see a table on inverses. And what this is allowing us to see an opportunity of what inverses look like from a table and a graph. Here's what's neat about inverses, and it's really going to make sense based upon the title. Inverses are your x become the y. So I'm going to write out my x coordinates. Down here is y coordinates. And your y coordinates become your x coordinates. So that's how you find the inverse from a table. You take the y and the x coordinates and you switch them. Now here's what it'll look like graphically. I'm going to graph the original function in red. So we've got 0, negative 1. We have 2, 0. We have 3, 2. And we have 4, 3. All right, and we just get some different points there for us to see. Let's now graph this one here in blue, which was the inverse. So it's negative 1, 0, 0, 2, 2, 3, and 3, 4. Now, what you might notice is there is a line of symmetry going through here. And this line of symmetry is occurring right here. You can see this kind of line moving back and forth. That's the reflection line. That line's equation is actually y is equal to x. And if you notice, other than that the size of some of my dots are a little larger than others, you'll notice that, these are equidistant apart from the reflection line. The equation that I drew there diagonal is y is equal to x. The most basic y equals mx plus b equation, right? To where the slope is 1, the y-intercept is 0. And this is actually how inverses relate. We set up here in the yellow that x's became y's. X's became y's. We said here for the y's that y's became x's. Y's became x's. And that's why the reflection line is y is equal to x. Because what we did to generate the data was we took the y-coordinate and the x-coordinate and we switched them. And we'll get to graph other various inverse scenarios throughout this chapter. And we'll see that the reflection line is always y is equal to x. We can also find inverses by hand. To find an inverse, so there's two ways that we'll look at it. The main way is going to be f inverse of x. You simply need to switch the x and y values and then solve for y. We can also denote it by saying y to the negative 1 power. And that's just going to let our readers know that we have found the inverse. So let's go through this equation and find its inverse. So it says the first step is to switch x and y. So I have done that. Right, let's all agree that I took this equation. This x is now y, which it is. This y is now an x, which it is. And we're tasked with resolving for y, which I would do by subtracting 1 on both sides. Then I would solve by square rooting both sides. So we are in an equation context, so we'll get plus or minus x minus 1 is equal to y. I'm now just going to go ahead and grab this guy and swing him back over here to the right, because we're used to seeing y is equal to on the left. It doesn't have to be, but that's just kind of how we're used to seeing it. But what I need to do that's going to be important is I now need to label this as y negative 1. That tells us that these two equations are inverses of each other. And anytime you switch x and y and resolve, you have found an inverse. So x squared plus 1's inverse is plus or minus the square root of x minus 1. So what we're going to do is we're going to take these and we're going to graph them at the same time, and we're going to answer this question of, is the inverse a function? Let's graph the original, and I forgot my minus 1 here. Make sure that you do note that this is a minus 1 right there. It's inverse. Let's graph the first one in blue, and you could type this in on your calculator or just plug in x values, but here is x squared plus 1. All right, it would create for us these points. So I'm going to draw these out. And this is our y is equal to x squared plus 1. And I'm now going to make a graph for plus or minus square root of x plus 1. Now, if you wanted to type this one in on your calculator, you'd have to actually do it twice. You'd have to type in the square root of x minus 1 and y is equal to the minus, because it was plus or minus, the square root of x minus 1. And it's going to look like this. And remember, I'm getting these I'm just plugging in x into the equations. But you could view these by, typing both of these into y equals. And then you can see we get the same reflection line of y is equal to x. So this diagonal line right there. And you can see that that is in fact happening. We have these equidistant reflection points. And then the other points as well. Okay, so we have confirmed that these are inverses because when I graph the two, they are reflected across the line y is equal to x. But it asked us, is the inverse a function? We know that this guy, yes, is a function. The original version of this was quadratic. So it is a function. This inverse, though, is not. And remember that functions have to pass the vertical line test. And if I just draw a random vertical line, say from here to here, I hit the green equation, the inverse, twice due to this plus or minus, which means the inverse is not a function. And that's why you've never seen or graphed sideways quadratics, because sideways quadratics are not functions. That's why you had to type it into your calculator 2 different ways to get it to show up. There is no one way to type it in to your calculator because it's not a function. So what this actually teaches us is that you can determine if a function's inverse is a function or not by using not the vertical line test, but the horizontal line test. So that would mean, even if you didn't want to make this graph, if I asked you about it, I could say, for this function here, y is equal to x squared plus 1, is its inverse a function? So not is it a function, we know it's a function, but is its inverse a function? Instead of graphing it and using the vertical line test, you could simply use the horizontal line test. The horizontal line test says no, the inverse is not a function. So just some things to think about. And the portion of this video here was just to help us understand visually what do inverses look like. They're reflected across the line y is equal to x. How do we graph them? How do we find them? We find them by taking x and y and switching their places. So let's look at this one. It wants us to find the inverse. Do keep in mind that f of x is the same thing as y. So that can help you better see that you need to swap the two. I've done my inverse to where you take x and y. This x became a y, this y became an x, and now I need to solve. And I would solve by squaring both sides. So I'll get x squared is equal to y minus 2. There's no plus or minus because we didn't take a square root. Plus or minus signs only show up when we take a square root. We have squared both sides. And then when I add 2, I'll get that x squared plus 2 is equal to y. I'm going to go ahead and once again swap this part to the other side. So y is equal to x squared plus 2. Back in the original problem, we took f of x and made it y. So I need to put it back as f of x. And we also need to put its negative up there. And this now tells us, I'm going to erase this so we can see it, that here's function f of x. Here is its inverse. And is it a function? Yes. This is quadratic. And you don't know how to graph this one yet. That's going to be in the next section. But this function is quadratic. It's x squared plus 2. So yes, it is a function.